Hello and welcome to section 10.2 part 2, the coronavirus edition. We're going to finish up working with 3x3 systems of equations. Part 1 of this looked a lot at one solution, that is where three planes intersect at exactly one point. But that's not all that can happen when you're working with a 3x3 system. You could have planes that are parallel, in which case there's no common point and no solution. Or you could have three planes that meet along a line, in which case there's an infinite number of solutions. So to help us remember a little bit about these things that can happen, we're actually going to look back at the 2x2 case for a brief moment. So one thing that can happen is that the two lines cross each other. And that's ideally what we'd like to see. We'd like to see one solution. That point, 4 and 2, can be checked. You can prove to yourself that this is the right solution by plugging it back into the equations. X is 4, plus 2 times 2 is 4 again. 4 and 4 is 8. Or 3 times 4 is 12, minus 2 is also 10. So it works in both equations, so it's a solution. And because it's a solution, the system has at least one solution. It's consistent, and the two lines are different from each other, so it's independent. Now, that's not all that can happen. You can have an inconsistent system. And you might notice from the equations here that both of these have a slope of 1/2, but different y-intercepts. So necessarily these lines are going to have to be parallel, and they won't cross. And because they don't cross and there's no solution, it's inconsistent. At the same time, it's independent. It's independent because the two lines are different from each other. They're not the same line. So that's yet another possibility. And the last possibility to consider is this one. So the equation 2x plus 3y equals 6 is graphed here. If I shut that off and turn this one on, you can see pretty much the same graph, right? In fact, if I turn them both on at the same time, this does get a little bit darker. You can see that really these two graphs are the same. So in that sense, this is a dependent system of equations because the two lines aren't independent from each other. But at the same time, there's an infinite number of points of intersection. That is, one line is right on top of the other. So there's an infinite number of solutions. Now, what's that mean in terms of solving our systems of equations? I'm glad you asked. If you have an inconsistent system, then when you try and solve, and here I solved it by substitution, I took the expression for y from the first equation and substituted it into the second equation. When you have that inconsistent system and we try and solve, we end up with something that's false. 2 does not equal -2. There we go. And that's false. And that's telling us that, okay, this is an inconsistent system. It's not going to have a solution. On the flip side of things, if we look at our dependent system of equations, then we can solve by multiplying, say, the top equation by -2 and adding it to the bottom equation. So, no, multiply by +2. +2 will work. Add it to the bottom equation, and we get something that's true. And that's the big difference here. If the variables cancel out and it's false, then it's an inconsistent system of equations. If the variables cancel out and it's true, then hey, you've got a dependent system of equations. Okay, that's great. What's this going to look like when we solve 3x3 system of equations? How am I going to know what's going on? Well, let's take a look at some examples. This is number 32 from your book. To solve a system of equations, we're going to start by picking a row and eliminating a variable from the other two rows. So the row that I picked was the one that starred right here. This one right there. And I'm going to use this row to eliminate the y from the other two rows. So for instance, if I add twice this row to the first row, that is 2 times row 2 added to row 1, you can see that work down here, then I get rid of the y's, and that's what I wanted to do. I wanted to get rid of the y there. Now you have to get rid of the y from the other two equations once you've picked this one. So here's a question for you. What would I multiply the row 2 by and add to row 3 to get rid of the y in that equation? So put in this question mark for me. What's that going to be? Well, hopefully you said 3. 3 times the second row added to the third row will cancel out the y there. And again, that's what I wanted. I wanted to get rid of the y from those two equations. And this is perfect. This is exactly what I was looking for. I was trying to get rid of the y from both equations because now this gives me a nice 2 by 2 system of equations, and I can solve this any way I want. I could graph this on my graphing calculator, I could use the addition method, or I could use substitution method. And just a quick FYI, a lot of times I use the term addition method as opposed to elimination method. Elimination method, I'm just not really fond of that term. Anyways, whatever you want to call it, we're going to multiply the first row by -2 and add it to the second row. And look, we get something that is false, right? So what's that telling me about my system of equations? That's not true. Since that's false, that's telling me I have an inconsistent system of equations. And that's the big thing to see here, is that if you have an inconsistent system, at some point your variables are going to drop out and you're going to end up with something that's clearly not true. Let's take a look at some other things that can happen when you're solving a 3 by 3 system of equations. Now, it's back in the first video that you actually find solutions for x, y, and z in terms of numbers. But there's other things that can happen as well. So let's take a look at example 34. In this case, I just chose the first equation, and I'm going to eliminate the x's from the next two equations. Now, when you're choosing equations and choosing a variable to eliminate, what I look for is something that has a coefficient of 1 or -1. For instance, I could use the first equation to try and eliminate the y's, but that's going to involve one of two things. Either the use of fractions or a lot more work in terms of multiplying the first row and the second row. So let's just keep it simple. Look for something that has a coefficient of 1 or -1. So to get rid of the x's, I'm just going to do the same thing twice. I'm going to multiply the first row by -2 and add it to the second row. That'll give me a -2x, and 2x gives me 0, which is what I wanted. And then you can see what happens with the other remaining variables. I end up with -y plus 4z equals 1. Now, whatever you get here, just set it aside for the moment and repeat this. We've got to eliminate the variable from two of the other equations. So I got rid of the x from the second equation. Let's use row 1 again to eliminate the x from the third equation. So notice you're using the same row twice. That's the one that I circled here in yellow. Now if I multiply row 1 by -2 and add it to row 3, then I get this equation circled here in purple. Let's put those two together, because those two together give me a 2 by 2 system of equations to solve right here. And you can solve that any way you'd like. This looks pretty much tailor-made for the addition method. And notice we get 0 equals 0 again. And I can't ever help Draw those little happy faces when I see 0 equals 0. That does mean that you have a dependent system. You're not going to be able to solve explicitly for x, y, and z. You're not going to get numbers, x equals this, y equals this, z equals this. But we can still do something with a dependent system. So we can do a little bit more than we could with our inconsistent system. Now from the second equation here, I can solve and get that y equals 4z minus 1. So I'm figuring out what y is in terms of z. And once I get that expression for y, let me plug it back in here and see what I get. So I'll plug in that 4z minus 1, and let's see. If I distribute the negative 2, and then collect like terms, so negative 8z and z added together give me negative 7z, subtract 2 and add 7z to both sides, and I end up with x equals 7z plus 1. So take a look here. I've got y defined in terms of z and x defined in terms of z. So I could write my solution x, y, and z. Z I'm just going to let be whatever. Y, well, y was 4z minus 1, so there you go. And x was 7z plus 1. So there's my solution. Nothing wrong with that at all, except for whatever reason, a lot of times books and WebAssign, instead of using a Z, they're going to want to use a T. And that would look like this here. So just replace the Z by a T and get that expression. Now, if you choose T equal 1, for instance, I'll get 8, 3, and 1. That'll be a solution. If I choose T equals 0, I'll get 1, negative 1, and 0, and so on. I could choose T equal negative 1 and end up with negative 6, negative 5, negative 1. I can get any number of solutions I want once I make the choice for this T. So that's one form of the solution. Now, if you're looking at this and going, oh my God, I'm just never going to get that. I am going to be doing something different this semester because we're not going to be able to use row ops as easily. I can't disseminate that program to everybody on their calculators. I'm going to be doing something a little bit different that's going to make getting these things a little bit easier. Actually, probably a lot easier. So we're going to invest in some technology, but that comes up in a later section. For now, let's just take a look at one more like this, and that's problem number 35. And part of what I want to do in problem number 35 is just review what you do solving a 3x3 system of equations. But honestly speaking, if this were me and I was trying to solve this as fast as possible, I'd probably take and notice that I'm missing a y in that second term, in the second equation, so that if I get rid of the y in the third equation, then I'll have my 2x2 system of equations. I'll end up with something that depends on x and z for those two equations. That is, if I eliminate the 6y term. You can do that pretty easily by multiplying this by what? What do I multiply row 1 by to eliminate the 6y here? If you said negative 2, great. Okay, that was a brief aside. Pardon me, indulge me, thank you. Let's go back to solving this. I'm going to do this. I'm going to use the first equation to eliminate the x from the second equation. I'm going to go back and use the first equation again to eliminate the x from the third equation. So what do I multiply the first equation by to get rid of the x here? Hopefully you're saying -2. And likewise, multiply the first equation by -4 here to get rid of the x from the fourth equation. And when I do that, I get these two equations. I get -6y plus 8z equals 4, and -6y plus 8z equals 4 again. Essentially, these are the same equation. So if you multiply these two together, or you multiply it and add, -1 times row 1 added to row 2, we end up with my famous 0 equals 0 again. So what that's saying is that I've got another dependent system. So because it's dependent, I'm going to see what I can do with this. And the first thing that I'll notice is that essentially I've only got one equation here. So let's work with that one equation and solve for y in terms of z. So I'll move the 8z to the right-hand side and then divide everything by -6. I get this expression. Okay, that's great. Normally you'd have to plug this expression back in here for y and then solve for x in terms of z. But we've got a nice alternative here. And our nice alternative is the fact that this equation right here, the second equation, doesn't depend on y in any way. So I can just get x in terms of z, which is what I did here. I moved the 4z to the right-hand side, it became negative, divide both sides by 2, and I end up with a nice expression for x. So I've got x defined in terms of z and y defined in terms of z. So keeping in mind, like before, this is x, this is y, this is z, I can just let z be anything. We don't have enough equations to determine an exact value for z, so z is just anything. That's going to happen when you have a dependent system. But y is defined. Here's my expression for y. 4z minus 2/3. So that's my expression for y. And then I solve for my expression for x over here. So x, y, and z. Now, if the book wanted to, they could ask you to write this in terms of t's, and that's fine. Let's see if we can't do that. Rewrite this in terms of t's. So we're going to replace z by t, and replace this z by t, and replace this z by t. So that's your equation in terms of a parameter t, and that's pretty awful. There you go, 2. So that's what's called a parameterized solution. Now, like I said, we are going to make finding these easier, especially in this Corona semester. But I hope that gives you a better understanding of what can happen when you're working with systems of equations. Like I said, the 3 different things that can happen. And part 1 of this video looked at intersections of 3 planes, giving you 1 point. Now we've looked at the other 2. An infinite number of solutions, that's your dependent, consistent system, and then no solution is your inconsistent, independent system. Good luck.